Hi, my name is Michael Radushkin, and this is Lab 3, Magnetic Field of a Bar Magnet. The presentation will go as follows. First, a brief introduction. Second, the setup of the experiment. Third, the results of the experiment. Fourth, a computational model supporting the experiment. And finally, a post-lab discussion. There are two main purposes to this lab. First is to determine the relationship between the magnetic field from a bar magnet and the distance to an observation point, specifically the exponent of which we set the distance, which we'll later find is negative 3.04. The second purpose is to determine the magnetic dipole of a bar magnet, which we'll find is 2.781 joules per Tesla. Some models and physical principles that we'll use throughout the lab include the general magnetic field of a dipole, or in this case, we use a magnet represented by the equation below, which uses the value mu, which is the magnetic dipole moment as represented in the diagram to the left. The magnetic field of a dipole on axis, which is both equations are simplified versions of the general formula above. The magnetic field superposition property, which basically states that at a certain position, different magnetic fields from different sources can be additive or subtractive, and also the concept of linearization, which will be used to determine the value k and the value n. And now on to the actual experiment. The system of our experiment is the magnetometer on our smartphone, and the surroundings include Earth, which provides a magnetic field, and the bar magnet, which also provides a magnetic field. The initial conditions of our lab include the bar magnet being perpendicular to the Earth's magnetic field in order to accurately measure just the bar magnet's magnetic field. The magnetometer is marked off on the phone, and also the phone for specifically part 1 is located on the axis to the bar magnet. Within the actual experiment, we move the phone along the ruler multiple times until 20, 70, 120, 170, and 220 microteslas was reached, and we repeated it 3 times and found averages for them. Then we determined the distance to reach 100 microtesla, and then moved the phone up perpendicular to that with the same distance and recorded the magnetic field of that measurement, which we used as our 45-degree measurement. And now onto the results of our experiment. After we recorded all of the data points, we applied the linearization principle, which was described earlier, by taking the natural log of each of the values and taking a non-linear trend and turning it linear. And using this, we were able to determine that the exponent with which our distance is set to is negative 3.04. Similarly, we were able to find this value of k, and plugging it in with our equations and setting them equal to each other, we were able to determine that the magnetic dipole moment of the bar magnet was 2.781 joules per Tesla. Now, this is the computational model that I used in order to model the experiment. I set 7 observation points, 2 which were on axis, 4 which were perpendicular, and 1 which was 45 degrees from the bar magnet, and determined the magnitude of the magnetic field of them using the general formula of magnetic field, which was brought up in the introduction. Specifically for the 45-degree angled observation point, we determined that the magnitude of the magnetic field was 2.66 times 10 to the negative 5. Now this is slightly off our calculated value within the experiment, which was 5.48 times 10 to the negative 5. However, they're to the same magnitude, which means they're still relatively close with each other, though there are slight differences because of possible errors, which will be brought up in the next slide. And now a post-lab discussion to end the video. Some possible errors that could have made our computational and experimental values for the 45-degree angle measurement different include potentially not determining the right location of the magnetometer in the smartphone, which could have set the distances differently, not moving the smartphone exactly perpendicular to Earth's magnetic field, thus having the Earth provide some sort of magnitude when we were just trying to determine the bar magnet, and also the magnetometer itself could have not been accurate. Now, which of these statements describe what we observed? What we observed was that when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction, and also that as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. So if we didn't account for the magnetic field produced by Earth, each value would have been consistently off from the bar magnet's actual value by some sort of proportion of the Earth's magnetic field. And if we were to stick two identical magnets together and run the experiment again, we would have roughly the same exponent value, but the measured magnetic fields at similar observation points compared to the original experiment would basically be double.